So let's talk about quantum number. So in quantum number, we have what's called principal quantum number, the azimuthal quantum number, the magnetic quantum number, and the spin or angular momentum. Spin quantum number, angular momentum. So for the principal quantum number is represented by n. And it describes the shell. The principal quantum number describes the shell. So we have the K shell, KLMN. We also have OP, but we just stuck to KLMN. So we have KLMN. This is first shell, second shell, third shell, and the fourth shell. So in this principal quantum number, there are maximum number of electrons that can be present in this shell. The principal quantum number describes shell. Understand? Shell, not orbital, shell. So the formula for the maximum number of electrons that can occupy the shell is 2n squared. So for the first shell, the maximum number of electrons, if you sub 1 into n, that will be 2. For the second shell, that will be 2 squared will be 4. 4 times 2 is 8. For the third shell, 3 squared is 9. 9 times 2 is 18. And this is 32. Because when we solve 4 inside, that 4 squared is 16. 16 times 2 is 32. So these are the maximum number of electrons that can occupy the principal quantum number. The shells of the principal quantum number. The principal quantum number. One thing you should know about the azimuthal quantum number is the azimuthal quantum number, it subdivides shells into subshells or orbitals. So it's the azimuthal quantum number that divides the shells into orbitals, and it describes the shape of the shells. So yeah, it describes the shape of the shells. Shape of shells. So the azimuthal quantum number, they are divided into subshells of S, P, D, F. And they also have maximum number of electrons that can occupy each subshell. So how do you calculate it? Using this formula, 2 brackets. Okay, one thing, the azimuthal quantum number is represented by L. Principal quantum number N. Azimuthal quantum number is represented by L. So to calculate the maximum number of electrons in each subshell is 2 brackets 2L plus 1. Most of us actually even know this in offhand, but we don't know it from this formula. So to get it, this is L, right? L. So to get it, this is 1, 2, subshell 1, 2, 3, 4. So just input 1. This is 1, 2, 3, 4. Input 1 into this formula, as 2 times 1 is 2, 2 plus 1 is 3, 2 times 1 is 2. Okay, yeah. So before I continue, there's one thing I need to know, that the azimuthal quantum number, the minimum value of azimuthal quantum number is 0. So 0 to n minus 1. Understand? 0 to n minus 1. So if the principal quantum number is 1, the azimuthal quantum number will be 0. If the principal quantum number is 2, the azimuthal quantum number will be 0, 1. You understand? So that being said, S will be 0, P will be 1, D will be 2, and F will be 3. Now, for the maximum number of electrons that occupy each shell, not to confuse you, let me rub this off. So the maximum number of electrons that is going to occupy each shell, just impute these numbers into this formula. So 2 times 0 is 0. 0 plus 1 is 1. 1 times 2 is 2. That's 2. P is 1. 2 times 1 is 2. 2 plus 1 is 3. 3 times 2 is 6. That's 6. D is 2. So 2 times 2 is 4. 4 plus 1 is 5. 5 times 2 is 10. And F is 3. 3 times 2 is 6. 6 plus 1 is 7. 7 times 2 is 14. So that's why we used to write the maximum number is S2, J2, S2, P6, D10, and F14, because these are the maximum number of electrons that can occupy each subshell. So that's what you need to know. We're also going to be solving some questions on quantum number. So the next quantum number you need to know is magnetic quantum number, and those ones they describe the orientation of the shell. They describe the orientation. So let's say they describe orientation. So let's say we have also orientation of the orbital, or they describe degenerate orbitals. I think the degenerate orbitals are orbitals that have. So we know azimuthal quantum number, they describe the shape of the orbitals. So magnetic quantum number just they give the orientation of the orbitals. They differentiate the orbitals. They give the orientation of the orbitals. And let's say azimuthal quantum number now. Azimuthal quantum number L is equal to 3. The magnetic quantum number will now be -3, -2, -1, 0, 1, 2, 3. So this will be the magnetic quantum number if the azimuthal quantum number is L is equal to 3. So that's how it is. And spin quantum number just gives the direction of how electron moves. It's either -half or +half. So, and that's why if you are writing it using Pauli exclusion principle, we write it this way: one is moving up and one is moving down. Let's say this one is moving up in the positive direction, this one is moving down in the negative direction. That was spin quantum number is talking about. So that's that on that. And there are also principles. There are principles guiding the right electronic configuration. We have the Ohm's rule, the Pauli exclusion principle, and the Albert principle. What Albert principle is saying that for electrons to be filled into an orbital, you have to fill the one with low energy before you fill the one with high energy, because it's called building. Albert principle. That's if you are building. So you need to build the foundation, that's one with low energy, then you build it on top to the one with high energy. So let's say we have something like this now. These are the orbitals. I want to fill in 5 electrons. So for Albert principle now, we need to fill the one with low energy first. So that we will fill it like this. We fill this one 1, 2, 3, 4, 5. This is Albert principle. But Ohm's rule now says electrons enter into orbitals singly before pairing, and for us to fill it, we need to fill the orbitals one by one before we now pair it. So Ohm's rule now says, let's say we want to fill 5 electrons. Using Ohm's rule, right? Then we have 1, 2, 3, 4, 5. You can say I first filled it once before I came back. But after we fill this one, then you fill this one, then you fill this one. But in Ohm's rule, we fill it, then you now come back for the pairing. You understand? Why Pauli exclusion principle states that no 2 electrons in the same orbital can have same value for each quantum number. Even if they have a value of quantum number, their spin quantum number is going to be different. Understand? So that's why we move it like this. It's not going to be like this. If it's like this, it's wrong because it's not following Pauli exclusion principle, because they cannot have the same value of all the four quantum number. At least their spin quantum number must be different. So if you are feeling, you feel like this. So that's what Pauli exclusion principle says. So that's the explanation for all the principles. That's the explanation for all the principles. So that's that on another quantum number. So there's this question in the slide. I'm coming. Let me check the question. So the question said you should find the subshell. Say find the subshell. After finding the subshell, you should find the number of subshell. Number of subshell. You should find the number of orbitals and the maximum number of electrons that can occupy, and maximum number of electrons. Number one, they say find the subshell. Number two, they say find the orbital. Number three, they say find the maximum number of electrons. Maximum number of electrons. And the principal quantum number of n is equal to 4. Right? This is very easy. I'll teach you the normal way to do it and the short form. The normal way, if they say find the number of subshell, what describes subshell? Principal quantum number describes shell, azimuthal quantum number describes subshell. So if n is equal to 4, azimuthal quantum number will be 0, 1, 2, 3. You feel me? So if it's 0, 1, 2, 3, that means the number of subshell is still 4 because this is 1, 2, 3, 4. So we answer question number 1. If n is equal to 4, if principal quantum number is 4, the subshell is also going to be equal to 4. Answer question 1. That's question 1. We answer question number. Question number 2. They said how many orbital. Now to find orbital, we are going to move away from azimuthal quantum number and go to a magnetic quantum number. So azimuthal quantum number, where did it stop at? It stopped at 3, right? So it went from 0, 1, 2, 3. So for magnetic quantum number, we do when m is equal to when L is equal to 0, magnetic quantum number is 0. When L is equal to 1, magnetic quantum number is minus 1, 0, 1. When L is equal to 2, magnetic quantum number is minus 2, minus 1, 0, 1, 2. And when it was equal to 3, you see the board? Yeah, when it was equal to 3, is minus 3, minus 2, minus 1, 0, 1, 2, and 3. You can see. So to get the orbital, we'll now count everything like this. Okay. This is minus 1. So to get the orbital, now count everything like this. So that will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So the number of orbitals is 16 orbitals. And number of orbitals. Number of orbitals is 16 orbitals. Now the next question is now maximum number of electrons. I've told you how to calculate maximum number of electrons. Let's do it. Number 3, say calculate maximum number of electrons. Can you see the board, please? So to calculate maximum number of electrons, just know maximum number of electrons is 2n squared. So just plug in n is equal to 4 into this equation. So that's 4 times 4. 4 squared is 16. Let's plug it inside. That's 2 brackets. 4 squared. That's 2 times 16 plus 4 squared is 16. So 2 times 16 is 32. So we've answered number 1. The number of subshell is 4. Number 2, number of orbitals is 16. And number 3, the maximum number of electrons is 32. But doing this in the fastest way. If you ask you to find the number of subshell, of course that one is fast already. But if you ask you to find the number of maximum number of electrons, that one is fast. But if you ask you to find the number of orbitals, instead of doing those magnetic quantum number, those -3, just square the principal quantum number, and I'll explain why. So if they say find the number of orbitals, if the principal quantum number n is equal to 4, the number of orbitals will be n squared. Yes, the number of orbitals is going to be n squared, and that will be 16. Let me now explain. Since the maximum number of electrons is 2n squared, right? The maximum number of electrons is 2n squared. The maximum number of electrons is 2n squared. That's the formula. And you can only have 2 electrons in one orbital. That means you're just going to divide by 2. That means the orbital will be n squared. You get it? So the orbital will be n squared. So just know it like that. So if they ask you that if n is equal to 5, what's the orbital? What's the number of orbital? The number of orbital will be n squared. That will be 25. And as easy as that.